Good morning or good afternoon, everybody, again, and welcome to our new appointment with the webinar series of the EMBS Technical Committee on Therapeutic and Diagnostic Systems and Technologies. My name is Paola Accomandi. I am the chair of this very nice TC, and today we have the big honor to welcome Professor Paul Meaney as one of our speakers. Professor Meaney received EBS in Electrical Engineering and Computer Science from Brown University in 1982 with a master's degree in Microwave Engineering from University of Massachusetts in 1985 and his PhD from Dartmouth College, and he spent 2 years as a postdoctoral fellow, 1 year at the Royal Marsden Hospital in England, and plus he spent many years in working in industry, so doing a lot of research on microwave-based devices for different applications, if I'm right. His research has focused mainly on microwave tomography, and he has been doing a lot of things during his research and during his professional journey in terms of application of his research on the biomedical side. So I don't want to take too much time on this and would like to welcome him and his talk about the portable microwave thermal imaging, technical advances, and phantom experiment results. So, Professor Meaney, the floor is yours.
Thank you very much. That was very generous of you. But I'm going to dive right into my presentation here. And okay. I first want to thank Punit Prakash. He and I have been collaborating with William Park at Thermomics LLC, I think, or thermomics.com, down in West Bridgewater, Massachusetts. They're developing a gel to kind of enhance heating through just basic RF ablation. And one of the things that came up in the second phase of their small business innovation research grant was they wanted to be able to image and really test if their gel was working. And I hadn't really done much thermal imaging stuff for at least 15, 17 years. But we really cut our teeth on thermal imaging before we even got involved with breast imaging. So Punit was really the one who said, Paul, you should try your imaging system. And we got some interesting results. And then he said, people are really interested in this. They hate doing MRI for temperature monitoring. So that's kind of where all this came about. I will give a quick warning that my background, I was really lucky to work in industry from about 1985 to about 1991, primarily at Militech Corporation. And I got to work with some really, really bright people, and we built all sorts of stuff. And I just got really into building things, testing it, validating models, and all sorts of stuff. So you'll see that, very much a lot of what I do has a heavy duty dose of hardware type stuff, but I hope it's interesting. So with that, I'm going to launch into this. I'm going to give a fair amount of history and why it's important to kind of the stuff, stuff that we're doing right now. Okay. And a lot of people have contributed to this. Keith Paulson is my long-term colleague, business partner, mentor. These are all a lot of graduate students. Eugene Demidenko is just an amazing mathematician. We had a program project grant from NIH that sponsored a huge amount of collaboration with, and you'll see that a lot of this work is intertwined with some of our breast imaging work. And so that was why we had a large component of people from the radiology. AIC is the Advanced Imaging Center. CSI is the Center for Surgical Innovation and stuff. So we've had a lot of people, and this really is nowhere near a complete list of people who've contributed to all this work. Okay, in terms of doing the thermal imaging, I mean the basic premise is you want to be able to integrate a thermal therapy with something that can monitor the treatment. So for microwave thermal imaging, you've got active imaging, which is what we do, but there's also passive radiometry. And in that case, you're looking at black body radiation differences with temperature. In our case, we're depending on the fact that the tissue dielectric properties change with temperature, primarily the conductivity, and we try to image it at different snapshots in time, and we can see the changes in the properties, hopefully, and that gives us some good information in terms of the heating that's going on. That I will revert back to in different points of my discussion. There's a lot of similarity between what we do with tomography and X-ray tomography. It may not seem it, but I'll kind of make the case as we go along that there are important aspects related to just basic CT. Um, First, one of the best examples of doing passive radiometry was by Paul Stauffer's group when he was at UC San Francisco. This is, going back quite a ways. But one of the things that was neat about this is you can see the sheet. There's basically a patch antenna, but then etched inside of it is a spiral antenna. And spiral antennas are really quite broad. So they would heat, exciting the patch antenna, but then the spiral antenna allowed them to receive black body radiation at multiple frequencies. And that radiation at those multiple frequencies allowed them to kind of get data at different depths and stuff while they were doing the heating. So this was kind of the front and back of just a sample of their circuit board. This is what it looked like with respect to an actual patient. You can see that they actually had a custom water bolus to keep the surface of the skin relatively cool while the heating would kind of radiate into the body where you really wanted the treatment to happen. This was really quite innovative, and they tested this on a number of patients. So this was pretty cool stuff. Um, Paul is now retired, but even when he was at Duke, they did a lot of good thermal therapy. Okay, so on to the active microwave imaging, and here, microwave tomography is used primarily or used widely for breast cancer imaging, stroke diagnosis, anywhere where the dielectric properties give a kind of an advantage. And one of the things is that the properties do change um, significantly with respect to temperature. In particular, the conductivity will change a couple of percent per degree C, especially at frequencies below 2 gigahertz. Above that, you start getting into the dielectric relaxation of water, which takes over the conductivity. But at these lower frequencies, it's really pretty interesting. So, we have, a mechanism we can exploit the varying properties, and we need to come up with a reconstruction algorithm, a configuration where we can do the imaging and tracking the temperature linearly is really, really important. So, and just kind of a quick thing on tomography. You want to kind of excite from all different directions. So here's an imaging domain. You can see the greenish shaded region is a scatterer. The little star thing here on the left is radiating out just isotropically. And when the fields interact with that scatterer, you can see all of a sudden that the fields get perturbed. And it's those perturbations that really have the information embedded in it with respect to this scatterer. And you can see that those perturbations are very different depending on the angle to which you excite the tissue. Um, and so trying to get an image from this type of information in the microwave world is a nonlinear problem. It's ill-posed, and that makes for some challenges and stuff. As opposed to, this is just kind of a simple schematic for X-ray tomography, and you can see that, there you're working with the rays are going straight through. That ends up being a much simpler problem. It's a linear pro and essentially a closed form solution for coming up with a um, for an image of that domain. So moving on, and I'm going to just kind of I like some of these older photographs. Gives a sense of where we've been. Uh, this is circa 93 to 95. You can see we really hadn't decided at that point whether we were going to use water-filled microwave waveguides or monopole antennas. So we were playing with both. We had a very large tank. Our antennas were kind of suspended into that large tank. We had quite a bit of custom electronics here. The network analyzer did not have the dynamic range that we wanted, and so it basically ended up just being the RF source for what we were doing. And I think above on the right is just a bunch of power supplies for all the microwave electronics. So we got pretty good at building custom electronics. And again, this plays back to my um, uh, my microwave hardware background. And as we move on, one of the things that we focused on, we chose monopole antennas. I could probably, kind of go off on that for, at least a day or so, kind of talking about the advantages. And I'm not going to bore you all with that. Just a couple of important points is that the monopoles, because they're so low profile, can be packed really, really close to the target. And they're also, very easily modeled. Some of the later things that we've been doing in terms of really making the reconstruction algorithm really fast, we now use this thing called the discrete dipole approximation, and it happens to really work very well with the monopole antennas. We do use a quite lossy liquid. In this case, for the breast imaging, we'll use mixtures of glycerin and water. For the thermal imaging, we tend to use more of uh, kind of saline things. It suppresses, all the multipath signals, evanescent waves, and because the antennas are resistively loaded, really gives us a very broad bandwidth to work with. So it gives us some significant advantage. One of the key issues is because of that lossy liquid, we have to use a very, very high dynamic range network analyzer, 140 dB, which is huge. Um, and we got pretty good at developing systems that not only gave that dynamic range, but then also gave the channel-to-channel isolation that's also required for something like, especially a multi-channel system. So it's th- that's a hard, spec to meet. But as I'll get into kind of the discussion of multipath signals, as hard as it is, it's easier than solving the multipath problem. So, and here's kind of a cartoon. What we've got is monopole antenna. You can just barely see the active part of the antenna. Above this line is a glycerin water mixture. Below that is just the plexiglass, and I've artificially changed the conductivity for these 5 different cases. You can see over here, the fields are just going everywhere. The fields are strong, but they're so out of control that it makes it really difficult to work with. As you increase the conductivity, i.e. making it more lossy, the field patterns get to be a whole lot more manageable. And by the time you get to this, quite high conductivity, there are no multipath signals, but the signal is lower. And so that's why we need this higher dynamic range system. But it allows us to work with a very, very well-behaved signal, and that's really key to our system working. So anyway, I just wanted to throw this out. This is something we worked on really quite early and focused on these lossy baths with the monopole antennas. Okay, a couple more photos. Here's a system, a full up system where we actually have 16 antennas. Again, we've just taken the previous electronics and we now kind of multiplex it here so that we can feed all 16 antennas. Each antenna can act both as a transmitter and receiver, so we can get 240 pieces of information. That's, each transmitter receiving 16 and then receiving at the complement of the remaining 15. So 16 times 15 is 240. Again, quite a bit of custom electronics. This is all, lab scale system, but it allowed us to get into this tank and really start doing some interesting phantom images. You can see we still have a very large tank, and the custom electronics is also quite large. This system only worked up to about 1 gigahertz, but it really was very, very important step for us. Um, and we took that system and we basically packaged it up on a couple of custom wooden carts. We made this was again geared towards the breast imaging, but we put the antennas in this thing. There's a bellows here, so you can see the bellows over here, and there's basically a car jack underneath it, and we could raise and lower the antennas so that we could image different planes of the breast. Um, the bellows was critical to keeping the system from leaking. And we have had more than our fair share of big spills of liquid and stuff. You can imagine this tank is big, and if that amount of liquid spills on the floor, it's quite a disaster. Well, we've had a couple of disasters. We can laugh at it now, but anyway. So once we put it all in these carts, we over here is our reservoir for the liquid. Put a tabletop on top, put some sheets and some padding and a couple pillows, and voila, it looks like a breast imaging system. So, but again, this was an important milestone. Right at about this time, we used this from 98 to about 2002. In about 2000 was when we got this program project grant that Keith Paulson led. And so we had some money to actually, do a little bit more advanced work. And so this was the first system. We no longer have the bellows. The antennas actually go through these hydraulic seals underneath. We have a computer-controlled motor that moves the antennas up and down. The electronics has been packaged underneath, in this cart underneath. Still, it's all custom, but it's a lot more advanced. We now can work up to about 3 gigahertz. Again, lots of padding. I think this system, we probably imaged about 350 women on it. So this system got quite a bit of airtime. You can see this cartoon, just the woman lying on the bed, breast pendant through this aperture here into the liquid, and then the antennas move up. We take data at different planes and we move the antennas down at 1 centimeter increments so that we can either get full 3D reconstructions of the breast or just multiple 2D tomographs of the breast and stuff. So again, this was an important advance. Some of the things, especially related to the breast imaging, that we developed was the glycerin bath. Depending on the ratio of the glycerin to water, we could we could tailor the dielectric properties of the bath. The different women had, extremely dense breasts, heterogeneously dense breast, on down to fatty breasts. And so it was, to our advantage to be able to get something a better match to each of the patients. Glycerin is great to work with. It's bacteria static. That means basically that bacteria can't grow in it. It's really comfortable to the touch, safe. It's not toxic, so it's great to work with. Um, and we started because of this lossy bath, we were able to kind of start getting a much more compact imaging system, less liquid. Again, the lossiness really was terrific in terms of suppressing the multipath signals. And the multipath signals in this case, type of imaging can be just absolutely debilitating. So um, this was, I actually had a small spin-off company. We built this commercial system. We spent quite a bit of energy on the breast here. You can see the tank is shrunk even further. There are two plates here. Each one controls 8 antennas. These little black things are our custom hydraulic seals. And again, the antennas move through the base of the tank. So, and these plates, each plate is controlled by two different opposing motors, so we can get 8 moving independently from the other 8. Again, being able to get cross-plane data was useful in terms of helping our imaging algorithm. And there's just another couple views of it and stuff. This was a really, we spent some serious effort and with this grant, some significant money in terms of getting this working, and it really was super for us. I think we imaged probably about 200 women with this system. Um, okay, so uh, this is just a quick cartoon of our reconstruction algorithm. We take data from we take our measurement data, the actual patient, the antennas and stuff, and this is the measured electric fields, the amplitude and the phase, and then basically we compare it to our model. We start with a guess of the properties, and we do this. We minimize this statement, and k squared is basically our image. K squared is the basically the permittivity and then the complex part of the conductivity. And I'm not going to get into how we do that, but basically what you end up, you take a guess of the properties, and then here's the computed electric fields, which you compare at each iteration with the measured values. And, at the first iteration, you get kind of a blob, but then you kind of start to see, some shapes sort of at multiple iterations, and you can kind of, oops, and eventually you see kind of the whole breast and then kind of some form of inclusion. So we've basically stuck with this. It's a Gauss-Newton iterative method, and there are other uh, uh, um, optimization routines. There's the distorted Born approximation. There's all sorts of genetic algorithms. One thing that's key to this is the primary term that we're interested in, but we also have a regularization term. The regularization is necessary because uh, uh, this reconstruction process is ill-posed and stuff, and we need that term to stabilize the reconstruction. Okay, again, this is our breast imaging system that we've used in the clinic. And okay, so finally, I'm getting to some thermal imaging, and which is what we're kind of all about. You can see this is actually the same configuration we were using with the breast imaging. Over here, all the electronics is underneath this wooden table, and we've got our imaging tank. The monopole antennas are passing through the base here. Now, what we did was we basically contrived this uh, PVC tube, and we just pumped saline through it at different temperatures. So you can see it came in here at the top, came out the bottom through these just different tubings and stuff. We did remove some of a large part of the walls of the PVC tube because we didn't think we could really image that well through such a thick-walled kind of object, and we just replaced those bits of the walling with mylar sheets, just enough to keep from having leaks and stuff. And we would send the liquid through, and we would basically wait till it stabilized at a given temperature. Then we would take our imaging data. Now, one of the big problems back then, this is probably early 2000s, was that our data acquisition system was not that fast. So it took us roughly about a minute to take the data. But given that we, could wait till this stabilized and stuff, a minute really wasn't that bad. But obviously, a minute is pretty painful if you're trying to do some serious dynamic thermal imaging. But there was some important things we needed to prove here. So this was a useful first stage. So we took these images and reconstructed the data, and then we looked at the properties in the center of the tube, or within the image of the center of the tube, and started analyzing that. And again, one of the things is, this is kind of obvious, but we need the properties to change linearly with temperature and all. We're pretty confident of that, especially at the lower microwave frequencies. There's a whole bunch of good data in Francis Duck's seminal textbook on the physical properties of tissue. And the other thing that's really important is that the microwave images need to be able to track linearly those property changes. And this is not such an obvious thing. And so just go, I'm using this configuration. This is real data. And what we did was we did a standard least squared algorithm. And by this, I mean, and I'm going to skip around a little bit. I apologize. But right here, you see this equation in the bottom. That's the electric fields, the measured electric fields and the computed electric fields. So that's one way of doing the reconstructions based on that. And so we got this set of data on the left. And then on the right, what I originally called it the LMPF, and that's log magnitude phase formulation, but it's basically the log transformation. And we tried it with 4 different regularizations, mostly just either pure Tikhonov regularizations or the Levenberg Marquardt, or kind of hybrids of the two. And so the solid line here is the actual dielectric properties changing, in this case, the conductivity changing with temperature. And then you see 4 other curves of the reconstructed images, also as a function of frequency. And this is the property, basically what would be at the center of that tube. And yeah, the reconstructed data kind of goes in the general direction, but compared to that straight line, it's not really very good and stuff. And you'd be a little bit hard pressed to use that for actually tracking temperature. Now, on the right, using our log transform, um, you've got the solid line, the actual properties, and then next to it, there's actually 3 superimposed curves, same as over here, with a different regularization, and you can see it tracks that conductivity just perfectly. One of the regularizations did not work very well. I want to show it for completeness purposes, but obviously we could select any one of these other 3 and just be in good shape. This gave us a whole lot of confidence. I mean, and it really showed the significance. I've been beating this drum for way, way too long, using this log transform, but this was an important result with real measured data showing that there's a significant advantage using the transformation over not using the transformation. And I'll make a quick point, because I do these comparisons with the X-ray CT. X-ray CT uses the log transformation, and it would not work without that log transformation. So this work using this log transformation goes way back. I love the two authors from the 50s and 60s. You can look them up on Wikipedia. Their names are Box and Cox. I mean, it couldn't be funnier. But they were very, very famous mathematicians, did great work, and this was fundamental to why, our thermal imaging was working so well. I'm going to move on to a couple quick phantom experiments we did way back, and then I'm going to get into some of our uh, more current stuff we're doing with Thermomics. Paula, how much time do I have?
Uh, it's you have 15 minutes more if you
Okay,
want.
okay. So I'm just going to kind of show some videos and stuff, and then I think I'll be good. Okay, I got really interested in doing focused ultrasound when I spent a year at the Royal Marsden Hospital in England, and one of the things is, we work with a lossy bath. So if you wanted to do, say, some heating with some, say, a microwave waveguide, that's not going to work because you throw a waveguide into a lossy bath, at a high power level, well, all the heat's just going to get absorbed right at the face of the waveguide. So, and to my naivete, I never even thought about doing it with thermal ablation. So I thought, well, what is lossy in the microwave frequencies is not necessarily lossy for ultrasound. So this is a phantom experiment. You can see our imaging tank down here, the microwave monopole antennas, and what we've got is uh, a, a focused ultrasound transducer, and it's supported by these three rods up here, and we can actually steer the that ultrasound transducer. And so this is just kind of a quick video of how we steer that transducer. This is a cone, but the cone is just kind of an example of where the focus point would be for our transducer. And um, so I'm probably gonna skip a little of this, but you can see, um, so you see the three motors moving up and down, and depending on how I tip the transducer, I can steer it. And the tipping is done by just moving the different rods underneath. It's kind of like a three-legged stool. You're just moving that. And so I'm going to skip through some of this a little bit just to kind of so again, there's the cone. So the here's the actual transducer. And again, it'll take it through its sequence, um, raise it up. And so you can see that the hollowed out bit of the spherical transducer, and that's what focuses the beam. And so we can focus the beam into the um, what you call it, the phantom. So um, okay, so again, this is just the phantom experiment. There's the transducer, here are the monopole antennas. And we took it through a couple of different examples of sequences of moving the beam around. First one was just we just went in a big circle, and so what I can do here, these are all difference images, and the transducer was just kind of focused and just keep repeating going around in a circle. And you can gradually see the heating going on, and finally it gets pretty strong, and gets big enough that it starts conducting away from that image, and then we get to a point and we turned off the power, and you can kind of see it goes more or less back to where it started, with no change in properties. So that was one example. Um, Here was another one. Actually, I'm going to skip this one because I don't. I'm going to run out of time. Um, okay, so this one, um, apologize. What it did was uh, it scanned not in a full circle, but just part of a circle and just kept going back and forth. Again, with the heating on. And so you can see, um, again, these are difference images. You can see that the C circle starting to show up, and then it gets hotter and hotter. Um, and then it gets pretty hot. It starts, you can see it conducting away. It's literally almost filling in that central area. And then we get to a point where we turned the heating off, and it just started backing off. It's kind of just a blob at this point, but it goes back almost to where it started from. So again, these are pretty neat images. Now, um, so the key thing here is, I think we really resolved a lot of the things needed to do the imaging, but the technology wasn't there. Um, you know, our data acquisition time was too long. 1 minute was crazy. The imaging tank was huge, hardly portable and stuff. Uh, the microwave electronics was very bulky, um, hard to work with. The image reconstruction, even at the fastest we got it back then for the 2D images, was about 15 to 20 minutes. But flash forward, the image reconstruction using this discrete dipole approximation, we can do the images in about 6 seconds. The data acquisition, we now use a Rhodian-Schwarz multi-channel system. Yes, it's expensive, but it can acquire the data we need for 2 frequencies worth of data in about 1 second. So this is, with the dynamic range that we need. And the imaging tank has been reduced significantly in size. So one of the things was I had never done anything with pieces of metal and stuff. And so we did some preliminary tests. Here's the agar gel. Here's our tank. It's really pretty compact. All of the movement underneath is just a simple gearing system. It's all made of plastic, very efficient and stuff. And we took the agar gel and just put a metal rod in it and just threw in different diameter rods and just saw what we looked at what we saw. And sure enough, here are the 5 different diameter rods. You can see the far left is just the agar gel. And you kind of, it's pretty close to the properties of the background. We had a 1.5 millimeter rod. Interestingly, it doesn't really show up in the conductivity, but it does show up in the permittivity, relatively pronounced. And as you transition to larger and larger rods, it becomes more and more pronounced. Finally, it starts showing up in these lower diameter rods. We did this because, the RF ablator is, pretty small diameter. It's kind of in this ballpark. So it's neat that we can use it, and it's the sigma, the conductivity images that we're really looking for the property change. So it doesn't look like it changes, it has that much effect on the conductivity image, i.e. the heating that we're most interested in. Um, Interestingly, just looking at the convergence behavior as the rods get larger and larger diameter, the convergence is not quite as good as we would like. So that's just another confirmation that, larger pieces of metal really do start getting challenging for us. But if we stay with the nice small ones, things can work pretty nicely. Um, Here's us, on moving day. We're going to West Bridgewater, Massachusetts. Here's William Park, our sponsor, with one of his students. Unfortunately, partially cut off there. But he's a happy customer. We're doing imaging. I had my car packed. Here's the Rhodian-Schwarz system. The tank, fits very conveniently in my car. I think the keyboard and the monitor are up in the front seats. I left my house at 7 in the morning. It's about a 3-hour drive. Arrived at 10:15. By 11 o'clock, we were set up, did the first sets of experiments, took a lunch break for an hour, finished up at 2:15. I was able to get back and miss the Boston rush hour traffic, and I was home at 6 o'clock and time for dinner. So, this has come a long way from where we were at previously. This is portable, sets up nicely, and we did some good experiments. Um, in this case, Thermomics is interested in what they call this heat sink gel. There's a little red dye in it, but basically we put it right next to the thermal ablator. And so we did one experiment where we didn't have the Thermomics gel, and we did one with it. And, and so, the setup on the bench, very compact, again, sets up really quickly and efficiently. And I won't go too far into some of the details, but you can see, the monopole antennas come up, surround this thing just where we want it to be. Um, Works like a charm. Um, this is just some measurement data. This is from one transmitter, which actually is in line with the ablator and the little cylinder uh, um, of the heat sink gel. And this is 90 degrees from that. And you can see, again, this is just the magnitude, the measurement data, and you can see that it's a little bit off balance, that the heat sink gel was probably having some effect. The key is, can we turn this, information, these changes in the magnitude data, into actual images? And so this is what I call the absolute images, the permittivity and the conductivity. This is with the heat sink gel, and it kind of looks like just kind of a circular blobs. You can't really make, but you see that it's obviously progressing in terms of the conductivity. Localized conductivity is increasing. We got sort of a similar thing without the heat sink gel. Again, it looks, these are the absolute images. Clearly, we're getting, the increase, local heating and stuff. But, what is it really doing in terms of uh, the temperature? So what we wanted to do was look at um, the difference image. So take the image at time zero, subtract that out, and see what it looks like. And so we're basically right at the end. This is without the heat sink gel, and I'll show you again. These are difference conductivity images, and oh, come on, stop. Um,
Uh, Paul, I'm sorry, I don't see anymore your screen. I don't know if it's me.
oh no, this is the punchline. You can't. Do you want me to stop sharing and maybe start again?
Can you stop sharing and start again, please? Yes.
Well, let me stop my presentation, and then let me see if I can. Oh, this would be tragic if you can't see this. Um,
Because you launched the video, right? Maybe.
yeah, yeah.
It's because
Um,
of this.
can you see that? No.
Mm.
Oh goodness, I don't know what to say.
Um,
Um, I can, I can certainly make this
okay, no,
presentation.
the others can see the screen, so maybe it's only my problem. Okay.
Oh, the other people can see it?
Yeah. Okay. Feel free to
Okay,
go
okay,
on.
good.
Okay.
Okay, I'm sorry, Paula, I'll send you the copy of the presentation so you can
No,
see
don't
it.
worry.
So anyway, so I'm basically, this is without the heat sink gel, and I'm going to start all over again. But you can see the heating it's offset a little bit from center, but it's relatively concentric, circular, which is what you'd expect with just an RF ablator type thing. It gets to kind of a point. It looks a little bit offset, but it's still pretty centralized. And now we've turned the power off, and it's starting to cool. Um, and it doesn't go all the way to the cooling, but it started to cool. Okay, so this is kind of nice. See, we see again, nice concentric heating, and it's monotonically increasing in that localized area, which is what we want to see. Now, the next is with the heat sink gel. Is the heat sink gel doing anything? And so with this, early on in the heating, it looks relatively um, concentric, circular, and stuff. But as you get a little bit further along in the heating, it does start to get kind of a pronounced, I think the overall area is actually relatively the same, but the heating is clearly skewed, or the peak heating is skewed to one side. And that's very much due to the presence of that heat sink gel. So again, we get the monotonic progression of the heating increasing, and now it's the heating's turned off, and I think it's just at the cusp of starting to start cooling down. So so anyway, this gives us, it gives us really a lot of confidence. First off, we can do the imaging uh, of the thermal ablation. I didn't actually really think we could do that, 15, 20 years ago. I thought the metal would really disrupt things. We see, the nice monotonic progression that what we really want. And we're also seeing that there is an effect from the Thermomics heat sink gel. There isn't a lot in there. When we showed it, they're just these little, like 5 millimeter straw kind of zones where we put this little gel in, but it's having a noticeable effect on this. So this matches up pretty well with some of Punit's early simulations and stuff. So anyway, I think this is actually kind of a neat preliminary result. I think that there's some potential, especially now that some of this technology has really matured. The measurement, reducing the size of the tank, the image reconstruction stuff was all done by my student Samar Hossein Zadigan when I was at Chalmers University in Gothenburg, Sweden. She did, really fantastic job. Now we can reconstruct those images in 6 seconds. These data acquisitions are really snapshots. They're, we average over 1 second and we take the data at roughly every 10 seconds. Um, so anyway, I think it actually all works really pretty nicely. I think there's actually quite a bit of potential for this, even maybe getting it integrated for patient stuff is a lot of work, but at this level, just some phantom experiments, I think it's really got a huge amount of potential. And with that, I will stop talking and let people ask some questions.
Thank you so much.
Should I stop?
You
Should
can
I
keep
stop?
it. You can keep the presentation on. Yeah.
Okay.
Yeah. People from the floor, I I welcome your questions, so feel free to ask. You should be able to open your microphone and ask the question directly. Yes.
Thank you very much, Paula. Can you hear me?
Yes, I can hear you.
Yes. Okay. Thank you so much, Paul. Like the presentation has been really inspiring. It's nice to see how the good work over the years finally paid off. And I have to say what you have done up to now is fantastic. I actually have a question regarding the phantoms. What
Mhm.
are your phantoms made of?
Oh, okay. In uh, so the phantom that we just used was just a very simple agar phantom. Instead of just water, we used 0.9% saline because we wanted it to be lossy so that so that the conductivity would change with temperature. We're doing all this data at 900 megahertz, so at that frequency we wouldn't see quite so much because the conductivity is relative is it's only just starting to increase around 900 megahertz. It goes up a whole lot more. But if you throw some salt in, and do it with saline, you get a much more pronounced effect of the heating.
Okay, and just another question related to the phantom. Do you know like how big can be your phantom to still get the signal of the changes induced by thermal, by the thermal damage, let's call it, or by the thermal change in the features of the phantom? Like
Yeah.
how large can it be so that you can still do this imaging?
I'm I'm sorry. I hate Zoom for this because I sometimes I can't hear very well.
Sorry, but I will try it again. Also, okay. So, do you know how big can your phantom be that you will still get signal strong enough to make this imaging?
Okay. You know, most of our imaging has been on a 15 centimeter diameter. So it's not huge. And you know, this all relates to the trade-offs with respect to, you know, a lossy bath and stuff. So, for instance, you know, as I mentioned earlier, a lot of our work was related to breast imaging. We can't get all breast into that 15 centimeter diameter, but we can get a lot into it. And actually, you know, I had that focused ultrasound thing aiming down at the phantom. We actually designed our system, but we didn't actually implement it where the ultrasound transducer could actually be underneath, come up from underneath the tank. So we could actually treat, you know, a patient lying on top with the breast pendant in the bath, and we could potentially treat, you know, heat, say, you know, a tumor lesion at the same time that we were imaging it. So, so yes, it's small. It's, you know, it works well for the breast. Larger anatomical sites like the, you know, a full torso would clearly be a whole lot more challenging. Although we have we have written a couple papers where we did some simulations and some experiments where we, you know, if we didn't have the antennas going all the way around, but maybe partially around, so that we could potentially have a water bolus around, say, the side of your torso, that we might be able to heat something. Anyway, so you know, the torso is always a bigger challenge for just about everything. But I think certainly as a starting point for doing phantom experiments, you know, for playing with different ablators and, you know, things like this Thermomics gel and stuff. This is, you know, it's really pretty good.
Yes, I agree. It's amazing. It's fantastic what you have achieved. Thank you so much for your answers.
You're welcome.
Thank you, Andrea. Punit, I saw your hand on.
Yes, yes. Thank you. Yeah. Uh, Thanks, Paul, for the very comprehensive seminar. That was very interesting. And the last question that was there with regards to size of the
Yeah.
volume that can be imaged, I had a similar question. I have a small follow-up on that. In the What's the sensitivity of this method, of this technique to motion? So if we're trying to image an organ that's moving, what are the challenges you foresee with that? And you've worked on any methods that could essentially correct for that?
Well, you know, that's actually a really good question. And you know, we do take advantage of, you know, difference imaging. And so that becomes a little bit of an issue, you know, for motion. Uh, you know, one thing, and this goes back a little bit to the previous question, we could potentially use a, you know, a larger diameter. What we'd have to do is go down in frequency a little bit, which may not be, you know, totally bad. Um, so there's always a trade-off between, you know, our dynamic range and how quick our snapshot is. So in this case, you know, we did snapshots on the 1 second type of thing. But if we could, you know, if we went, and that gave us down to a dynamic range of about, say, minus 125 or so. If we wanted to go, say, 10 dB larger dynamic range, we'd have to make the time 10 seconds longer, um, or go from 1 second to 10 seconds. But we could play games. We could go to a lower frequency where the attenuation isn't quite so heavy, and so that would buy us a fair bit in terms of the dynamic range. So we could potentially shorten uh, the snapshot time. And I'm thinking that if we get where the snapshot is maybe not quite real time, but a small fraction of a second, each image might differ in terms of the motion, but you'd get a truer snapshot in time. So that might be one way to mitigate it and stuff a little bit. Yeah.
Okay. Thanks. Yeah, I think that makes sense, and like I think you can see where my question is going. I think together with the what you shared about a partial coverage of an area around the torso, and then
Yeah.
looking at sort of faster imaging, I think these are interesting things to explore potentially for monitoring abdominal organs.
Yeah, I think it's possible, but anytime you're doing integration with a thermal thing and the monitoring, it is challenging. So, but I think what we've advanced in terms of reducing the size of our imaging tank, you'd have to kind of contrive it in a way that it'd be more of a bolus type of thing that would wrap around the body. But eminently doable.
Yeah. Yeah. Cool. Thank you.
Yeah.
Thank you, Punit. We have a question from Kathleen.
Hello?
Hello, Kathleen? You can speak?
She's not muted, but I can't hear her.
I don't know why.
Right.
We'll try a bit later again with Kathleen. Then we have a question from Emma. Emma, would you like to ask your question directly?
Yeah, sure. First of all, I would like to thank Professor Meaney. Your seminar was very, very interesting, and the topic of microwave imaging is new to me, but I've played a little bit with phantom making and the word of its difficulties and challenges. And that's why I would like you to ask if it's possible to explain again what is the advantage of using this heatsink gel and how this temperature information is useful to enhance the reconstruction of the image that you're acquiring.
Okay. Well, with respect to the heat sink gel, Dr. Park had he runs a small company and he won a grant from NSF. And so he's trying to get data that will confirm that, the heat sink gel really can change the distribution of the heating and improve, the heating for, whatever they're trying to treat or ablate and stuff. He's working towards getting FDA approval for his gel. So he needs to, a couple things he needs to prove to the FDA. One is that it's safe, but one is that, another is that it's actually doing what they think it's doing. And, what he thinks it's doing is altering the heating pattern. And so if he can, between what we're doing with the phantom experiments and the validation from Punit's simulations and some of his phantom experiments, this goes a long way to proving efficacy for the FDA. So right now we're very much in kind of a support validation mode for him and stuff. But later on, as Punit was alluding to, getting feedback data during any kind of thermal therapy can be very useful because you can potentially tell what regions are being heated, what regions aren't. If the heating isn't getting sufficiently to where the tumor is or what is, you can real time hopefully change that. And so this is getting, starting to get pretty darn close to being real time, or enough so that it could be useful in a clinic. As I said, the snapshots are on the order of 1 second. The imaging algorithm, is we can do it, get an image in 6 seconds. That's just with a simple laptop running MATLAB. So there's a lot of optimization and stuff that can go on there, and even that 6 seconds was data that was quoted from about 2021. So even just the sheer improvement in computation power will probably have brought that down some since then. So this all gets to the point of being real time, potentially giving real time feedback to the technician slash doctor in terms of what treatment they're doing.
Thank you very much. It was very clear.
Okay.
Thank you, Emma. Paul, we have 3 questions more. So if it's okay for you all, we go a little bit over the scheduled time, but I think it's important that attendees ask you questions. So if you agree.
Shoot. Yeah, go.
Okay, so we have Matteo, then we have the question from Vicky CPA, and
Thank
then
you.
yes.
Good morning, Professor. Thanks for your presentation, first of all. And I'd like to ask you one question about the reconstruction.
Mhm.
So, do you reconstruct absolute temperature or just differential temperature? I'm asking this because we know that microwave imaging works well in, say, finding small variation of complex permittivity, and also to have better reconstruction, we need to do a background measurement. So the question is, do you reconstruct just delta permittivity and then you convert it into delta temperature? And also, which kind of background measurement do you do? You do measurement at temperature 0 and temperature 1?
Well, I consider our images to be absolute images, although the calibration process does require, taking a measurement of the bath with nothing in it. But that, is just a one-time, takes, a minute or two to take that data. But we take what I call, absolute images. So we reconstruct the absolute permittivity and reconstructions, and then we take the image at time 0. We use that as a baseline, and we subtract the images at the subsequent, we subtract the time 0 image from the subsequent images at, we did them at every 10-second intervals, and that difference image is what we present. Now, as I said, these are full 2D quote full wave image reconstructions. So we're not kind of doing any. I've seen different algorithms, at different times, playing with just looking at just the differences and stuff. We're ours. I think ours is a relatively fundamental, straightforward reconstruction. We have a lot of experience with it. We've been using it for breast imaging for many, many years. And again, we've done a lot, in the last 5-7 years to optimize and make it really pretty darn fast.
Okay, thank you very much.
Yeah.
Okay. Now there are 2 questions in the chat. I will read them for you. The first question is, what are the isotherm readings on the images?
I don't know. And well, right now I'm focused on the recovering the dielectric properties. So these are differences in the dielectric properties. Now, converting them or mapping them into temperature is something that needs to be explored. Um, and different tissues, different liquids have different coefficients of uh, properties with respect to temperature. So, some tissues might have, you know, um, coefficient changes on the order of, say, 2% degrees C, where others might be 1% degrees C. So that there is some, a little bit of gray area, and that's something, people can certainly play with. I think getting the images first to start to, real images and think about that mapping, that's something that, people can start playing with. But I think getting the images in the first place is a really important first step.
Thank you. And the other question from Kathleen, who had problems with the audio before. So, about your discussion of the phantom temperature experiment, you mentioned that you needed to be able to linearly track property changes. I was curious about how your team decided on the four regularization schemes you tried. Also, perhaps this isn't relevant, but is the dielectric property change as you're ablating the tissue nonlinear? Does that impact on the temperature tracking ability?
Okay. Well, we never, to my knowledge, we never got to a point where we were ablating things. And, you know, ablating. So, for instance, with uh, the Thermomics heat sink gel, when that gel gets above a certain temperature, it turns into uh, it coagulates and stuff, and so its properties no longer are linear and stuff with temperature. So we haven't really gotten to that point, so when you start ablating things, that kind of takes you into a different world, because the properties will change differently with temperature. They're no longer liquid or semi-liquid and stuff. So uh, anyway, yeah, that is a important thing. We're clearly primarily focusing on pre-ablation type of state of things. But I think that's, that even in a therapy kind of setting, you want to know, where the heat's going, how much heat's going there, and you want to know it before you get to the stage of, the actual ablation. So I think even in that realm, I think it's still pretty valuable.
Thank you.
Okay.
I do also have a question, which is the spatial resolution you can achieve with your setup?
Oh, resolution?
Yeah, resolution,
Okay.
the special one.
Resolution is kind of a funny thing. It's not, perfect. It's certainly not an MRI image per se. Although I do have a big project right now where we're actually combining the microwave with the MR for breast imaging, and that's actually pretty fascinating. We generally talk about, 1 to it goes with frequency. So down at 900 megahertz, we're probably 1.5-ish kind of centimeter-ish type thing. But, again, going back to that graph where we showed, the very good correlation with the dielectric properties, the reconstructed ones versus the actual, I think the analysis we did on that paper way back was, the temperature accuracy was on the order of, point 2 or 3 um, uh, degrees. So it's really, really very good. So yeah, there's a lot of smoothing going on. That's all related to, the what goes on with the regularization process. But I think there's I think with the different stuff is quite powerful. And as I showed in the presentation, when you looked at the absolute images, you couldn't really tease out too much difference between when the heat sink gel was there and when it wasn't. But when you started looking at the difference images, it really became quite apparent. So again, looking at the difference type stuff is pretty powerful. But you have to start with something, you need to start with a good image. And I think that's, and a good image that tracks linearly. And I think that's where we're at.
Thank you. Thank you so much, Professor Meaney. It was
Great.
an insightful presentation, and I personally also appreciate a lot the journey that you share with us, because sometimes we forget what all these steps, all the milestones reached in the past, all the efforts we've done. So I really enjoy it, and I'm sure that all the attendees they did, because they asked many questions. So
Well, I think the historical side of it is actually valuable because a lot of good things were determined that really make some of this important things that make some of this work. So it really was just a matter of getting a faster network analyzer, getting a smaller tank, um, figuring out ways to speed up the reconstruction. But I think they built on a really solid foundation of what we were doing previously.
yeah, congratulations, really, congratulations. Thank you again for your time,
Yeah,
for your availability in this complex moment.
yeah.
Yeah, thank you so much.
You're welcome. I enjoyed it.
Great, great. Let me thank also all our attendees, participants. Yeah, as I already said, the recording of the webinar of Professor Meaney will be available on YouTube. I will share with you also the link.
Okay, great.
Thank you so much again.
Okay,
Have a great
thank
day.
you. You too. Bye.
Thank you. Bye bye. Bye bye.
Bye, thank you.